Welcome to Aneiro Acústica. This evening I will show you how to build your own sound level meter using a digital MEMS microphone. With this device, one can do some basic sound pressure and reverberation time measurements. Here is the list of the items you will need. MEMS microphone. In my case, I'm using two microphones from a model called MSM2061S. Tinsy 4.0 microcontroller, some wiring to connect the devices, a mini protoboard, a micro USB cable to connect Tinsy to the computer, and, if you like, a 3D printed case to put it all together. Mount Tinsy on the protoboard and make the connections according to this figure. It might be a little tricky, but be patient. Fit the model pieces and we are good to go to the software matter. For signal processing, you will need the following software: Arduino, Tinsyduino, Python, and Pita Toolbox, which is a package for acoustic and vibration processing. I won't show you how to install Arduino or Tinsyduino since there are other tutorials showing how to do so. Once you have it all installed, open the Audio Design tool to generate an Arduino code for Tinsy, or simply download it from the GitHub repository I left on the description. Then, connect the device to the computer and load Arduino code to Tinsy. Be sure to select the right port. This process may take a little while. Good, it looks like the process was a success. To check if the microphone is working properly, test it with Audacity or any other audio software. Hello, can you hear me? Can you hear me? If it's capturing the sound, we can jump to the next step. After installing Pita Toolbox, open Python to start doing some measurements. For SPL measurements, I wrote 3 codes. One contains useful functions. One serves to calibrate the microphone and record sound, and another to make the SPL calculations and plots. This code was set up to record 2 channels separately, but it can be modified according to the user needs. The function Pita list devices shows the sound devices connected. Use this to select the Tinsy port. In my case, Pita listed Tinsy as the device number 3, so we're gonna change it here. Okay, since we have everything already set up, let us test if the code actually works. Write the name of the measurement over here. Then it will ask you if you want to calibrate the equipment. This step is of great importance. Any mistake and the results given by the code will be completely wrong. There are 3 options to make calibrations the right way. Use the calibrator like the type 4231 along with a coupler for the MEMS microphone. Either use the same calibration signal I uploaded to the GitHub repository. But be aware that this solution is only adequate if you use the same microphone model I'm using in my prototype. Or, as a third option, one can use the info available in the microphone datasheet. The acoustic overload point, AOP, is the maximum acoustic level the microphone can read, meaning that the device will deliver 0 dB fs when the levels are higher than AOP. Write the sensitivity offset based on this information. In my case, the offset value is 30. Hit Y if you want to calibrate, or N if you don't. Once it is calibrated, you can now actually start the measurement, hitting enter. The measurements will be saved on a different folder, and now we can go to the signal processing. Choose the folder which contains the measurements you want to analyze. It will open the measurement and the calibration signal. Then simply run the code and see what happens. The first graph over here is from the calibration signal. These are the weighting curves and the sound levels over here. That's it. The measurement was a success. For reverberation time, there are two codes. One is meant to generate a sweep signal and record the decaying sound, and the other to plot the results. Okay, so to measure the impulse response, let's run the cells, generate the sweep signals, choose the folder name and select the correct devices. Then let's create a new impulse response take by running this cell over here. Run, and we can start the measurement here. It's possible to split the measurements into several averages, which is what I'm doing here. After finishing the take, don't forget to save it, and it will be right here. This file over here is the measurement we just did. Okay, now let's plot the results and see if the measurement was a success or not. It will import the beta object and do the calculations. It may take a little while, but we got the results over here. This measurement was done on a reverberant room, so we can see that the reverberation time is really high. Thanks for watching. Check the GitHub repository for more details, and feel free to modify it and use it for any purpose you like.